on this computer. Okay, good. So let's go. Today we cover section 13.10. This is the last section of chapter 13, Lagrange multipliers. What is it? Let's see our objectives. Our objectives in this section will be to understand what Lagrange multipliers are and to understand the method of Lagrange multipliers, and use Lagrange multipliers to solve constrained optimization problems. Optimization problems are problems regarding maximum and minimum. If you have a problem which uses maximum and minimum value of a given function, whatever that function is, that is called optimization problem. And we want to constrain, we want to solve that problem under certain constraints. So what are those constraints? We'll see. Use the method of Lagrange multipliers with two constraints. So there could be, we could be having one constraint or maybe two constraints. So unfortunately, this method of Lagrange multipliers is too tedious. So we are not able to do a lot of examples. We will do one example for each. That's already takes a lot of time if we have to solve it really in detail. So, but this example is enough to describe the method. So these two examples are enough to describe the method. So let's do it, Lagrange multipliers. Now, many problems of solving maximum and minimum have restrictions. You solve a maximum and minimum problem under certain restriction, okay? For what values of x and y is x times y is less than or equal to 10? Well, you may say x is greater than 0, y is greater than 0. That's one restriction, okay? You may say, oh, we must have x plus y less than or equal to 10. That may be another restriction. So we will put restrictions on a given problem, okay? That is what we are going to face. The method to solve such problems is called method of Lagrange multipliers. Let me, oh no. Okay, so let's keep it here. Now, to see how this technique works, suppose we want to find the area of a rectangle of maximum area, to find the rectangle of maximum area that can be inscribed in an ellipse. A rectangle is said to be inscribed in an ellipse if all the four vertices of the rectangle are on the ellipse, like in this picture. For example, in this this rectangle is inscribed in the ellipse. All its vertices are on the ellipse. So we want to find the area of the maximum area of this rectangle. Obviously, there is a constraint. You cannot make the rectangle large as you wish because its vertices have to be on the ellipse, okay? So here is a situation. Let's assume that the vertex of the ellipse, the center I'm sorry, the center of the ellipse and also the center of the rectangle is the origin, okay? We lose no generality by saying that. And let's consider one vertex. One vertex obviously will be in the first quadrant. Suppose the coordinates of this vertex are x and y. What that means is, the length of this side is 2x, because the distance from here to here is x. The distance from here to here is x. So this distance is 2x. And therefore, this distance is 2y. And therefore, if we call f to be the area of the rectangle, f of xy will be 2x times 2y, which is 4xy. This is called objective function. This function is called f of xy is equal to 4xy is called objective function. Our objective is to maximize this function, to find x and y, which makes this function maximum. That's our objective, okay? And this objective is obtained under this constraint. X and y, which will maximize this equation, should also satisfy this equation. That means they have to be, that point has to be on the ellipse. So this function is this curve is a constraint curve, okay? This curve is a constraint curve. And another constraint, of course, we just want x and y to be in the first quadrant, okay? Because it doesn't matter, right? It doesn't matter. The others are just for the purpose of finding the area. That one point in the first quadrant is enough in this case, okay? So now, to solve such a problem, we will come to this problem in a minute, but let's establish the background principle, the underlying principle we are using, okay? So the methodology, the Lagrange method, which we are going to use, is based on this theorem, which is called Lagrange's theorem. Lagrange is, by the way, used to be famous don't remember if it is I think it is 19th century French mathematician. He has a lot of discoveries. If you go in many fields, I know there is a Lagrange theorem in physics. You may see a Lagrange theorem in other fields. I don't know about computer science, but in mathematics, his name shows up a lot of times, not just in calculus, but in other branches of math. So in any way, this Lagrange multiplier is in the honor of this this French mathematician. So now, here is what the Lagrange theorem says. Suppose f and g, let f and g have continuous first partial derivatives such that f has extremum at point x naught y naught. Extremum is, as you know, maximum and minimum on the smooth constraint curve, g of xy is equal to c. Smooth curve means it has all the derivatives, okay? It has the derivatives. It is differentiable. That's what we mean when we say smooth. So these are the conditions. If the gradient of g at x naught, y naught, which is a vector, by the way, is not the zero vector, then Lagrange's theorem says there is a real number lambda, this is a Greek letter, lambda, such that del of f of x naught, y naught is equal to lambda times del of g of x naught, y naught. Lambda is a number, okay? So what does this say? This simply says, if these conditions are satisfied, okay, then del of f of x naught, y naught, which is a vector, is equal to lambda times del of g of x naught, y naught, which is also a vector, which means the two vectors, del of f of x naught, y naught and del of x naught, y naught, are parallel. They are in the same direction, okay? They are in the same, well, parallel, the same direction if lambda is greater than 0, in opposite direction if lambda is less than 0, but they are parallel, okay? This theorem, theorem 13.9, gives the necessary conditions for the existence of such multipliers. Necessary conditions. What are the necessary conditions? F and the g must have continuous first partial derivatives, right? And f has extreme on x naught, y naught on the smooth curve. This curve must be smooth. G of xy is equal to c. This is a constraint. And that del of x naught, y naught is not the zero vector. If these conditions, these are the conditions, these are called necessary conditions. So Lagrange's theorem says, if these conditions are satisfied, then there is a number lambda which satisfies this condition. In other words, they are parallel. The two vectors are parallel, okay? So this is not used in practice. This is the theoretical foundation of what we are about to do, okay? The previous theorem gave us the groundwork for this procedure, okay? This is method of Lagrange multipliers. Method of Lagrange multipliers, okay? Now, look at this carefully. This is most important than the previous theorem. Let f and g satisfy the hypothesis of Lagrange's theorem. Let f have a minimum or maximum subject to the constraint g of xy is equal to c. This is a curve, right? To find the minimum or maximum of f, look, you will be given f, or you have to derive yourself like in the previous example, okay? You will be given, but you will be given the problem. Probably you have to derive the function f, but you will be given the underlying problem. So you will be, basically you are given f, and you are given the constraints. And you want to find what? You want to find the minimum and the maximum of this f under this constraint, okay? To do that, you use these steps, 3 steps. You use these steps, 2 steps, okay? 2 steps. The first step is solve the equation del of f of x y is equal to lambda times del of g of x y, which is obtained from the previous theorem. Remember, the previous theorem says this is satisfied. And the other constraint, this. So This is equal to that, this is equal to this, and this together give us these three equations. Why? Because the first component of this one, which is fx of xy, the first component of this one is equal to the first component of this one. The first component of this one is fx of xy. The first component of this one multiplied by lambda is lambda times gx of xy, correct? That's one equation. The second component of this one, which is fy of xy, is equal to lambda times the second component of this one, which is lambda times gy of xy. So this is second equation. So we have one equation, second equation, and the third equation is the constraint equation itself. So we have three equations in three unknowns. What are the three unknowns? Lambda is unknown, x is unknown, y is unknown. So if you have three equations in three unknowns, you can solve it, okay? You can solve for the three unknowns. So solve these three equations simultaneously, okay? And then if you solve this equation simultaneously, let's say you get, x1, y3, I'm just saying. And let's say you get x negative 2, y5, I'm just saying. This is not true, I'm just giving you an example. And let's say you get x0, y 7, I'm just saying, okay? So now, what do? Evaluate f at each of these points. Put x1, y3 in f and calculate, put x negative 2 and y5 and calculate, put x0 and y7 and calculate. The maximum of the value of f obtained from here will be the maximum value of f. You don't use lambda. You don't use lambda. You use just the points, okay? The minimum value of this is the minimum value of f. That's how you do it, okay? That's how you do it. So two steps. First, solve these three equations. Solve for x and y. And first, of course, you have to solve lambda as well, but you don't use lambda. You are looking for the x and y that satisfy these three equations, okay? Then plug in these solutions in f, and the greatest of those values is the maximum. The smallest of those values is the minimum. That's it. Now, so that's how you find, that's the Lagrange, the method of Lagrange multipliers. That is how we do it. Now, let's see how this problem's in an example, okay? Let's see just the previous example, the example we did, the example of finding area of a rectangle, the maximum area of a rectangle whose vertices are on an ellipse, or which are a rectangle which is inscribed in the ellipse. And well, we put the condition that x greater than 0 and y greater than 0 for convenience, okay? So find the maximum value of f of xy is equal to 4xy, which was the area of that rectangle, remember? Where x is greater than 0 and y is greater than 0, subject to the constraint, x squared over 9 plus y squared over 16 is equal to 1. So the first thing you need to do is find g of xy. G of xy is this function, okay? X squared over 9 plus y squared over 16. That's g of xy. Okay, of course that is equal to 1, but what you need is g of xy equals x squared over 9 plus y squared over 16. That's what you need. Okay, that's the function g, and this is a function f. Then what do? Use this equation, del of f of xy. Del of f of xy is fx times I plus fy times j. What's fx? Fx is the derivative of this with respect to x. It is 4y. 4y times I plus fy is the derivative of f with respect to y. It is 4x times j. And lambda, based on the previous procedure, we need to have also lambda times del of g of xy. Well, g of xy is 2x over 9. 2x over 9 times lambda I plus gy of xy is 2y over 16, which is y over 8, times lambda, which is lambda y over 8 times j. So what do we have? We need to have the I component equal to the I component, okay? So this is here, the first component equal to the first component. So 4y is equal to 2 lambda x over 9. This is equal to that. 4x is equal to lambda y over 8. Okay. Lambda y over 8. Okay. And what else? This one, this curve, this is our constraint. Okay. The second constraint is this one. So we have 3 equations, okay? 1, 2, and 3 equations, and 3 unknowns, lambda, x, and y. Now we can solve, okay? From the first equation, let me go back. From this equation, you can solve for x in terms of y. From this, and you can put that value in here. You can solve for x from in terms of y, and put it in here. So if you no, I'm sorry, not solve for x, but solve for lambda. I'm sorry. Solve for lambda from this equation and put that value of lambda in here. So what do you get? Solve for lambda, you get lambda is equal to 18y over x. Put that 18y over x in place of lambda in the second equation, and then you get if you solve this, you get this nice relationship. Okay, x squared is equal to 9 over 16 y squared. Okay, let's keep this one and put that value of x squared in this equation. X squared is 9 over 16 y squared. So if you put 1 over 9, this is 1 over 9 x squared, but in place of x squared, if you put this, plus y squared over 16 plus y squared over 16 is equal to 1. So everything is in y squared. So what you get is y squared is equal to 8, right? Y squared, 2y squared over 16 is equal to 1, which is y squared is equal to 8. And if you take the square root, you get y is equal to plus or minus square root of 8. Square root of 8 is 2 root 2. But you don't need the negative, as you know. So y is simply 2 root 2. Okay. y is 2 root 2. So, but x squared, we know so from the previous, if you remember, you know that x squared is 9 over 16 y squared from here. So if you put instead of y squared 8, if you put 8 instead of y squared, what you get is 9 over 16 times 8, which is 9 over 2. So x squared is 9 over 2. So take the square root of 9 over 2, which is 3 over root 2. So x is 3 over root 2. How about y? Y is 2 root 2. Okay. So that's it. We have x square root of 2, y 2 root 2, x 3 over root 2, y 2 root 2. So if you put that value of x in 4xy, you get 4 times x, which is 3 root 2, y, which is 2 root 2. And if you solve this, what you get is 24. Okay. 4 times 6, which is 24. Root 2 and root 2 will cancel. So the maximum value of f is 24. And it occurs at the point 3 over root 2, comma, 2 root 2. All right? So that's how you find the maximum and minimum value using the method of Lagrange multipliers. If you have one constraint, okay? Remember in this example, we have one constraint. That one constraint is x squared over 9 plus y squared over 16 is equal to 1. Or the vertex must be on the ellipse, okay? The vertices must be on the ellipse. Now, what if we have two constraints? Two constraints. We may require the vertices to be on the ellipse as well as something else, okay? So we usually, in real world problem, we do not have just one constraint. As a matter of fact, we will have several constraints, okay? We will solve a problem based on several constraints, okay? So let's consider the case of two constraints, and then you will have a good tool to extend it to several constraints, right? If you know this method, it's just expanding the same methodology to several constraints. So suppose you have two constraint functions, g and h. Previously, we had a constraint function g. Now we are adding another constraint function h. Okay. Then you can introduce a second Lagrange multiplier. Call it mu. That's a Greek letter. Those of you who I think you must have seen mu by this time a lot of times, but we use it a lot in statistics. So mu is a mean in statistics, but you must have seen it since you have taken a lot of maths classes. You must have seen mu a lot. So in any case, mu, and then we solve the equation. Now the Lagrange theorem now becomes lambda f del f is equal to lambda times del g plus mu times del h. Okay, so imagine if you have 3 constraints, 4 constraints, 5 constraints, it will go on the same way. okay? So where the gradient vectors are not parallel. If they are parallel, of course, then the problem becomes trivial. So in any case, that is the main difference, okay? Now, the other thing is absolutely similar, okay? But we will have two Lagrange multipliers to find when there is two constraints. Now, I'll simply give you one example on this, and then we will be done, okay? So this is example 5. Let T of XYZ equal to, T stands for temperature, T of XYZ equal to 20 plus 2x plus 2y plus z squared represent the temperature at each point on the sphere. X squared plus y squared plus z squared is equal to 11. The question is, find the extreme temperature on the curve formed by the intersection of the plane x plus y plus z is equal to 3 and the sphere. So we are finding the maximum temperature on the sphere, okay? But we are not really finding the maximum temperature on the entire sphere. Instead, we are finding the maximum temperature on the sphere, which is and the intersection of the plane x plus y plus z is equal to 3. So those points must be on the sphere, and they must also be on the plane, okay? In fact, the intersection of a plane and a sphere is a circle, right? So we are finding points which are on the circle, which is the intersection of the plane and the sphere, okay? So that is the problem. So how do we solve this problem, okay? So we use, first of all, what is our function g? What's our function h? Our function g is this one, the sphere. G of xyz equals to x squared plus y squared plus z squared. Now remember, t and g and h are functions of 3 variables in this case, okay? They are all functions of 3 variables. So we are going to have to use x, y, and z, which means I, j, k for vectors. So g of xyz is equal to x squared plus y squared plus z squared, and h of xyz equals x plus y plus z. So these are the functions g and h. Now you have to find delta t, del of t. Del of t, if you go back, del of t is simply fx, which is 2, fy, which is 2, fz, which is 2z, right? So del of t of xyz is 2i plus 2j plus 2zk, okay? Del of g of xyz times lambda, of course. As you know, del of xyz is fx, fy, fz. Fx is 2x, fy is 2y, fz is 2z. But we have to multiply by lambda. So it will be 2 lambda x I plus 2 lambda y j plus 2 lambda zk. Okay? And similarly, del of h of xyz times mu, of course. Del of h of xyz will be fx, which is 1, Fy, which is 1, Fz, which is 1, of course, times mu. When you multiply by mu, it will be mu I, mu times 1, which is mu, mu times j, mu times k. Now, you have to find equations now. You have to equate the I components, okay? This one is lambda g, lambda times del g plus mu times del h. So 2 is equal to 2 lambda x plus mu. 2 is equal to 2 lambda x plus mu. Again, 2 is equal to, let me watch this carefully. 2 equals, this is lambda t, is equal to 2 lambda x plus mu here. This 2 is equal to 2 lambda y plus mu, okay? What else? 2z equals to 2 lambda z plus mu. So what we get is here from this one and here from this one, okay? And we have two other functions, don't forget them. The constraint functions, what are they? X squared plus y squared plus z squared is equal to 11, that's the sphere. And there is another one, x plus y plus z is equal to 3, that's the plane, okay? So we have how many equations? 1, 2, 3, 4, 5 equations. How many unknowns? 5 unknowns. One unknown is lambda, another unknown is mu. The other 3 unknowns are x, y, and z. So we have to solve 5 system of 5 equations in 5 unknowns. You can solve that. Okay. Let's go, well, this could be tedious. I have to warn you, solving this kinds of equations, if you were to do lots of problems like this, don't be surprised if you struggle a lot to find, because, you know, as the number of unknowns increase, the number of equations increase, the complication also increase, but eventually you will find it, okay? So now let's see how we solve this one. If you subtract the first equation, if you subtract the second equation from the first one, here, you see 2 minus 2 is 0. 2 lambda x minus 2 lambda y is 2 lambda times x minus y. And the mu minus mu is 0. So from these two equations, you get 2 lambda times x minus y is equal to 2 minus 2, 0, this minus this is 0. That's what you get from the first equation, okay? From this equation, if you bring this one to this side, from this third equation, what you get is 2z times, if you bring this to this side, 2z, and factor out 2z, you get 2z times 1 minus lambda then bring mu to this side, minus mu is equal to 0. So that's what you get. Okay. So that's what we are getting here. Look at here. Okay. That's what we are getting. And what else do we have? We have the two other equations. So now from the first equation, what we have is either lambda is equal to 0 or x minus y is equal to 0. From this equation, what you have is from this equation, what you have is either lambda is 0 or x minus y is equal to 0. X minus y is equal to 0 means x is equal to y. Okay? Let's take lambda is 0. Okay? Suppose lambda is 0. Then what do we get? If lambda is 0, let me go back. I would like to go back. Okay? If lambda is 0, put lambda 0 in here. If lambda is 0 from this equation, if you put lambda is equal to 0, you get mu is equal to 2, right? So if lambda is 0, mu is equal to 2, okay? And if lambda is 0, let me go back again. If lambda is 0 from here, from this equation, let me, if from this equation, if lambda is 0, if lambda is 0 from this equation, we get, if lambda is 0, we get 2z is equal to mu. Two z is equal to mu, which means mu is no, z is no, which means z is mu over 2. Z is mu over 2, but we just said mu is 2, so this is 2 over 2, which is equal to 1. Okay, so z is 1. Now, if z is 1, this implies if z is 1, what we have is if z is 1, y is equal to 3 minus x. In this equation, okay? And if z is 1, this will be x squared plus y squared is equal to 10, because z is 1, 11 minus. And in place of y is equal to 3 minus x, in place of y, put this 3 minus x. So this becomes a quadratic equation, okay? So I'm just giving you a hint how you can complete this. Now you can find x, y, both x and y, okay? If lambda is 0, okay? If lambda is 0, you can, and then mu will be 1, mu will be 2, I'm sorry, and x will be, z will be 1, and you can find x and y from this equation. So I will leave the details to you. Let me erase this. Sorry about that. I'm doing this because this will show up in the video later. Although we are erasing it now, whatever we have done is recorded in the video, and the fact that we are erasing now is also recorded, so you will see what is going on when you see the video. So, I mean, if you get stuck, I don't get you'll get stuck, but who knows. So anyways, that's how you find so if lambda is 0, well, this slide simply says x is 3, y is -1, z is 1. We already found how z is 1. X is -1, y is 3, z is 1. So if lambda is 0, we get this one and this one. How about if x is equal to y? How about if x is equal to y? Let's go back, okay? If x is equal to y, then if x is equal to y, if x is equal to y, from here, we get 2x plus z is equal to 3. Right? So z is equal to 3 minus 2x. If x is equal to y from this equation. Okay. If x, so z is 3 minus 2x, but x is equal to y, from this equation, I can, instead of y, I can put x, so that it will be x squared plus x squared. So it will be 2x squared plus z squared, but z is 3 minus 2x squared is equal to 11. Now this is quadratic equation. You can solve this, right? You can solve this. This is quadratic equation. So you can solve for x, but x is equal to y, so it doesn't matter. And then you can find z. So that's it. That will solve the case where x is equal to y. I'm sorry, let me erase this. Okay, so if x is equal to y, so if you solve the problem we just saw, you will see that x and y are equal, of course, equal to 3 plus or minus 2 root 3 over 3. And z is equal to 3 minus plus 4 root 3 over 3. So let's see. So how many points do we have? We have 3, -1, 1, and -1, 3, 1. What does this say? This one says, let me write it exactly in coordinate form. Let's write it together. What does this mean? This means x is 3 plus 2 root 3 over 3, comma, 3 plus 2 root 3, because x and y are the same, right? Over 3. Then y, z is 3. When this is plus, this is minus. So it will be, z will be 3 minus 4 root 3 over 3. So you have to see the order. You see, this is plus minus, this is minus plus. Okay? So that's why this is plus. When this is plus, this is minus. And the other one is 3 minus 2 root 3 over 3, comma, again, y is also the same, 3 minus 2 root 3 over 3 over totally 3. And then when this is minus, this will be plus. It will be 3 plus 4 root 3 over 3. So you have to find the function t. You have to evaluate the function based on the Lagrange method. You have to find t at 3, negative 1, 1. You have to find t at negative 1, 3, 1. If you do, you will find both of them to be 25, okay? And before we go, let me eliminate this mess. So what else? The next one will be if you put the second equation, which I showed you, this was the second number. If you put this one for x, y, and z in t, you will get 91 over 3, which is 13.33. If you put this number, again, the other number, you will also get 91 over 3. You can check this. Okay, you can do that. So if you compare these three numbers, of course, 25 is the minimum. So the minimum temperature on the sphere, on the intersection of the sphere and the plane, is 25. And the maximum temperature on the intersection of the sphere and the plane is 91 over 3. Okay? So that is a curve, okay? The intersection of the sphere and the plane is a curve, okay? So the temperature on the curve is 91 over 3. All right. So these two examples, I hope, will be enough. If you do this example, other examples, they may have some, you may have some difficulty based on the nature of the equation, but the procedure is the same. So hopefully you can do any other problems. But I have to warn you, this section is probably the most section which will kill your time. Solving one single problem will take a lot more time than any other section. So, but I don't think we have a lot of problems in the quiz. So the reason why I'm telling you is if you are doing the quiz, I think I gave enough time, but you need to, you know, you shouldn't assume to do it very quickly, or keep in mind that it will take time, and therefore give it whatever time it requires. So I will eliminate this. So did anybody else join us, or only one of us? Were you guys listening to me, or I'm just talking in the open air?
We're listening.
We're listening.
Okay.
We're listening.
All right. So any questions? We have gone for about an hour, a little less than an hour. So I think we are done for this section, and we are done for chapter 13, which is differentiation of functions of two variables, or partial derivatives to say. Now the last chapter will be chapter 14. Chapter 14 we will begin next week. That is integration of function of two variables. We'll talk about double integrals and triple integrals as well. Okay, so if you don't have any questions, I guess we can end this class right now. And have a great weekend. See you next week on Tuesday.
See you next week.
See you then.
See you.
Bye.
Bye.